Thank you very much for the introduction. So yeah, actually, my name is Nicola. You can call me Tita. And today, I would like to present you some recent experiments we have been working at in Jacqueline Bloch Group in collaboration with Said Rodriguez from the Amos Center in the Netherlands, and with Alberto Amo, who is now working in Lille laboratories. So the protagonists of this talk are going to be these coupled microcavities, which nonlinear dynamics we are able to steer into a regime of parametric instability. So in order to get to this kind of microstructures, the starting point is epitaxially grown semiconductor heterostructure. So these structures are a versatile platform for nonlinear optics. And indeed, we can consider, for instance, a high finesse Fabry-Perot cavity, where we embed a quantum well at the cavity antinode. And then if we tune in resonance the electronic and cavity transition, we can have repeated cycles of absorption and emission before one photon is able to escape the cavity. And then in this case, we can effectively describe the excitation of this system as hybrid light matter quasi-particles, which we call polaritons. And because of the matter component, this system inherits a large kernel linearity, meaning that the effective refractive index, which is defining the cavity resonance, is going to depend on the local electromagnetic field density. So if we plug this into the resonant frequency and we Taylor expand it, this will correspond to additional term in the Hamiltonian, which will take this form in a second quantization picture. So this term is responsible for two main effects. The first one is a energy-dependent, a density-dependent energy renormalization of the modes. And the second one, instead, is a parametric interaction, which means that we can destroy two excitation from one mode and convert them into excitation in two other modes, often called signal and Euler, provided some energy conservation and phase matching conditions are met. Another important feature that we have in semiconductor microcavities is that actually, by profiting from the semiconductor microfabrication techniques, we can, well, in our case, it's going to be electron beam lithography and dry etching. We can mold the refractive index landscape of this microstructure, and we can use this in order to tailor the transverse mode of the system nearly arbitrarily. And now what I find interesting is that by combining strong nonlinearities, and so the possibility of having wave mixing with the possibility of engineering the mode of our resonators, opens a very interesting playground for nonlinear quantum optics. Two examples are, for instance, the idea of using ring resonators where the optical modes are equally spaced in energy, thus allowing to cascade wave mixing processes and then generating optical frequency combs which span an octave in wavelength and have very important implication in metrology. Or, as we saw yesterday, for instance, by leveraging the topological protection of topological edge modes, we can fabricate robust and integrated sources of quantum light. So, especially because of the large kernel linearity of Polariton systems, they seemed a promising platform where to realize integrated optical parametric oscillation, and especially which were energy efficient. So one first configuration could be the case where one considers just to pump at the inflection point of the lower Polariton branch. And then in this case, at the, pumping at the inflection point, energy and momentum conservation is automatically met, and one can trigger parametric oscillation. And then other, let's say, realization have been done by further engineering the dispersion relation in double and triple cavities, but also, for instance, considering different subbands in 1D wires or equally spaced modes in 0D pillars. And the common denominator in all this implementation is the fact that all of these are triply resonant schemes, And unfortunately, they either show a limited parametric conversion efficiency or extremely asymmetric sidebands. In this way, limiting the applicability for practical purposes and hindering the correlation between the signal and Eiler fields. So today I would like to show you that actually leveraging both effects related to the interaction term, it is possible to trigger a parametric instability in coupled microcavities where actually we have just a doubly resonant scattering channel which is opened. And the outline of the talk is going to be a quick recap of which and how to probe the transverse mode of these structures. What is the stability diagram of these coupled microcavities, and what is their nonlinear response under a strong quasi-resonant drive. And then I will show you evidence for this, the emergence of this parametric instability. And I just want to signal that this was theoretically predicted in this paper, but was never observed so far. So the fundamental building block for these coupled microcavities are micropillar resonator, where light is essentially vertically confined by the presence of two distributed Bright reflectors, and is laterally confined by the high refractive index contrast between the semiconductor and air. This results in discrete eigenmodes, which we can resolve in energy and position resolve photoluminescence experience. And then when we put two of these micropillars in contact, we will have a finite spatial overlap of the bare eigenmodes in the two pillars. And this in a minimal tie binding pictures corresponds to the fact that we will have a coupling term because we will have a finite possibility per unit of time for one excitation in one pillar to jump in the neighboring one and vice versa. And this will lead to the hybridization of the two bare pillar eigenmodes to form linear superposition of the two. Actually, the lower one is going to be called the bonding and corresponds to the symmetric superposition of the two modes, and the higher energy one is going to be the anti-bonding mode and corresponds to superposition of the two modes out of phase. And the way we can probe this mode structure is just by shining a continuous wave laser on top of the structure and recording the transmitted pattern. So here, for instance, you can see that indeed when we scan the laser frequency, we can observe two marked resonances, which splitting is telling us what is the coupling constant, and also we can resolve what is the transmitted profile at the two resonances. So the first one you can see that corresponds to the bonding mode, and the second one at higher energy corresponds to the anti-bonding mode, as signaled by the fact that in between the two pillars we have a zero intensity due to the fact that the phase in the two pillars oscillates out of phase. And then once we can also fit this data with a coupled mode model, and this allows us to fully characterize the linear properties of the system. So if now we want to study the nonlinear properties of this system, we can start with a semi-classical Langevin equation describing the amplitude of the fields in the two microcavities. And these are essentially described by the sum of two terms. The first one is deterministic in nature and corresponds to a drift term. And the second one is stochastic and is associated to the fact that we have dissipation in the system. So the drift term, in the steady state, the drift term essentially defines a set of algebraic equations which are giving us the expectation values of the intracavity fields. And then what we can do in order to assess the stability of this solution is to introduce small perturbation about the stationary solution. And if we plug this into the equation of motion, we linearize the equation, we pass into frequency domain, we can see that the evolution of small perturbation, which is essentially forced by these random terms due to diffusion, is going to be encoded in the spectrum of the Jacobian of the drift term. And then what we'll have is that if we have one eigenvalue of this Jacobian, which has an imaginary part greater than 0 and a non-zero real part, this will correspond to instability, which has an oscillating character. And then, because we have nonlinearities in the system, this will mean that the resonant frequency of the resonator will be modulated over time, and thus it will generate a parametric instability. So here what I show is a phase diagram as a function of the laser detuning and of pump power. And in the left panel, you can see the number of solutions regardless of their stability. And you can see wide areas where we have multiple solutions. This is well-known fit of a nonlinear system. And in the right panel, instead, I plot in this phase diagram the number of parametrically unstable solutions. So the idea now is to perform an experiment, for instance, exciting in correspondence of the antibonding linear resonance, and to scan the power across this parametric instability region and see if we can observe it. So in order to do this, indeed, we just accorded the continuous wave laser into one of the two pillars and pumped in vicinity of the antibonding resonance. And then upon careful calibration, we can use the transmitted pattern coming out to deduce the occupation numbers in the two cavities. So here I plot the cavity occupation in the driven and undriven cavity as a function of pump power, both when we increase and decrease the pump power. So you can see that indeed, as you scan towards this solution, so when we are increasing power, at some point we will jump up to a second branch of solution, and then by reversing the direction of the power scan, we will jump back here. So this is just an hysteretic cycle, which is a features, which is due to the fact that we are crossing a region where multistability is present in the phase diagram. And the dashed line instead here, you can see it's just the prediction, the steady, essentially the expectation value of the occupation number in the two cavities, which we predicted from the drifter. And you can see that it fits essentially very well for both branches, made exception with this point. And well, since this is a steady state prediction, we can already foresee that these solutions are kind of implying the existence of some dynamical feature in the system. And indeed, what we can do afterwards is just to study the stability analysis of this solution along the lower branch. And what we get is that this solution indeed corresponds to a region where our theory predicts the existence of a parametric instability with a modulation frequency which is matching more or less the coupling constant between the two cavities. In order to further assess this, let's say, characterize this instability, what we did then was just to look at the spectrum of the emission as a function of pump power. And indeed, you can see that below threshold, we have a single tone emission. And as soon as we reach the threshold for this instability, we have the appearance of two well-contrasted sidebands, which are indeed separated by roughly 2 times the coupling interpillar coupling strength. And I would also like to point out that the color code I'm using here is in linear scale, which means that if we look, for instance, in detail at the spectrum here, I'm plotting here in log scale as a function of energy, the spectrum, you can see that the sidebands which are generated by this process are extremely well contrasted, and they're roughly equal this time in amplitude. And on top of that, you can also resolve some of the harmonics of the process, and we can model very well our findings using our couple mode theory, including vacuum fluctuations. For those who prefer to reason in time domain, this, let's say, frequency spectrum corresponds, if you go in the frame rotating at the pump frequency, to the formation of limit cycles for the two intercavity fields with a typical period of 24 picoseconds. So, and now, in order to further understand a little bit what is the more deep physical meaning and what is happening, what we did was to just resolve the spatial profile of the emission. And we look at the spatial profile, and together with the total interaction energy in the system, also as a function of pump power. So if we consider the, let's say, quasi regime of pump power below threshold, you can see that the interaction energy is still much smaller than the coupling constant. And this means that essentially we are still pumping near resonance the antibonding mode. And indeed, the emission is single tone, and we see that it has the characteristic antibonding profile presenting the two lobes. And then as soon as we go at a threshold, you can see the emergence of these two sidebands. And if we look at the field, we can see that they present the bonding and antibonding profile. So in order to understand this, actually, it's quite simple. If one looks at the interaction energy, you can see that at threshold, the interaction energy becomes roughly equal to the detuning of the laser and so the coupling constant, which means that we can draw this cartoon where essentially because of interaction, we will be blue shifting the energy of the modes. And at threshold, what we have is that the pump sits in the middle of the two nonlinear bonding and antibonding modes, and thus we'll be able to scatter resonantly into the signal annihilator. So to summarize, what I wanted to say is just that we can build an efficient and low threshold parametric oscillation, because the threshold power here was just 300 microwatt, more or less, with nearly identical contrasted sideband. And then there is no need in general for a triply resonant configuration. Actually, what you just need is to have strong interaction, opening a resonant scattering channel, and then provided there is a sufficient mode overlap between the pump, the signal and annihilator modes, and strong enough interaction term, meaning larger than the losses, this will lead to a stimulated generation of sideband fields. And what I personally find interesting is also that this kind of mechanism is quite simple and I believe also quite general. And you can imagine to use this as a building block to just scale it up to more complicated situation, for instance, in microcavity lattices, where I believe that the same kind of reasoning applies. So for instance, you can imagine to consider these lattices of these honeycomb lattices of coupled microcavities, which you know has this characteristic direct cone dispersion relation. And if you imagine to use the same reasoning, you have that if you pump at the center of the gap, due to the fact that you have a linear dispersion, let's say the lower, the part of the dispersion which sits below zero energy and the one above are perfectly symmetric. So each state on the two opposite sides of the direct cone should be able to undergo this process. And this could be, for instance, interesting since there is an interesting phase structure of the wave function to have a structure of OPO emission. To conclude, I would like also to point out that this physics of parametric instability is not restricted just to resonant driving scheme, but it has also been predicted and observed using coupled condensates. So I believe it's pretty general and there is a lot of interesting things to find out. And with this, I would like to thank you for the attention.
Nicola, thank you very much for this interesting talk. Are there any questions? I see Alexander.
Yes, hello. Thank you, Nicola. I have the following question. So everything for parametric instability depends on the nonlinearity. And usually nonlinearity we have as a combination of nonlinear coefficient and occupation. So what I was wondering, since you have two modes, is it possible to come up with a measurement of nonlinearity which excludes the information about occupation? For instance, by having a difference between occupation in one mode and another mode, and deducing the nonlinearity from the, let's say, phase boundary.
I think, well, thank you for the question. I think actually is very interesting. I had not thought about it. I mean, we are always thinking about getting some, let's say, uncalibrated or self-calibrating way of measuring the Polariton interaction, because I know that this is still a hot topic to really have a precise way of determining it. But no, I didn't think about using this process. But yes, since it's a pair process, I guess that probably Yes, I think it should.
It requires thinking,
possible. Still, for the moment, I mean, at threshold, you rely on the fact that you need, for instance, I guess, to determine threshold power always via calibration, and these calibrations are extremely sensitive in our system.
Just in Sarche's paper, the phase boundary is shown as N2 over N1, so maybe it is possible.
Okay. Okay, thank you for the hint.
Thank you.
Okay, thank you, Alexander, and thank you, Nicola, for this interesting talk.